Hello folks, welcome to the first video on linear relations. So in this video, we'll introduce the idea of linear relation and look at a few examples. My first example here, we have a pattern, right? And math is made up of a lot of different types of patterns. We have different ways of describing certain situations, and there's a lot of overlap between some of these patterns and the equations that come with them and real world scenarios. So we're going to look at a few of these examples of one type of pattern that can help us describe some examples of real world scenarios. We call these linear relations. So what is linear relation? So let's get into it. So if we're looking at this image right here, we have a pattern that is made up of yellow and red squares. And I want you to notice two things that's happening here. So if we pay attention just to the yellow squares for a second, what I want you to notice is that in the first image, we have 6 yellow squares. And then in the second image, we have 6 yellow squares. And then in the third image, we have 6 yellow squares. So if I were to write a fourth or draw out a fourth image, we would assume that it also has 6 yellow squares. Right, so we notice here that the yellow squares actually don't change. There's always 6. We have this constant number of yellow squares, no matter which figure I'm talking about. The red squares, on the other hand, in the first image we have 1, and then in the second image we have 2, and in the third image we have 3, and we can again assume that what will happen is in the fourth image we'll have 4, and so on and so on. And this is the kind of the basics of these linear relations, is that usually there will be something that stays constant. That thing doesn't change, and something that does change. So in this case, the yellow squares stay constant, but the red squares are changing. And we have a number of ways of representing this in terms of expressions and equations, and we'll look into that. So here's another example. So we have a landscaper who's using wooden boards to edge a garden. So the green space here is my garden, and then the black lines around it are my wooden boards. So if we're looking at the first plot, when there's only one, we see that we have 4 boards that it takes to outline that plot. And then the second plot, or that is now 2 of them, we have, again, that initial 4 boards that it took to do my first garden, right? 1, 2, 3, 4 of them. But then to that, we have another 1, 2, 3 boards, right? And if we look at 3 plots, again, what we see is we have 1, 2, 3, 4 boards that it takes to outline my initial garden. And then we add another 1, 2, 3, and then another 1, 2, 3, right? So we're adding 6 on this time. And then if I look at my floor 4 plot garden, 1, 2, 3, 4, again, is that first 4 board plot. And if you had to guess how many boards we're adding to that, look at the pattern: 3, 6, and then next number is probably 9. Well, let's count and see. 1, 2, 3, 4, 5, 6, 7, 8, 9. There you go. So again, what we see happening here is that we have this constant, this thing that doesn't change. 4 for 1 plot, there's 4 for 2 plots, there's 4 for 3, there's 4 for 4, and so on and so on. Then there is something that does change. We have 3 when there's 2 plots, and then we need 6 boards when there's 3 plots, and then we'll need 9 boards when there's 4 plots. And you have this constant rate of change, this add 3, add 3, add 3, add 3. So usually what ends up happening at this point with these types of questions is we now want to describe them by using a couple of different strategies. First thing that we're usually going to want to do is we're going to want to use variables, right? We want to use something that is representing the number of boards or the number of plots. So in this case, we might use the variable b to represent the number of boards, and we might use the variable p to represent the number of plots. You don't have to. Like, usually we see x's and y's used a lot, but because we're talking about real objects, we can usually use the first letter of those objects to say these are the letters that are going to represent them. And then if I wanted to describe this pattern, so what is the pattern? Well, if I look at the actual number of boards in each of these things, I have 4 boards, and then 7, and then 10, and then 13, and so on and so on. So if I wanted to describe these things, I could use a picture like I see at the beginning, but I could use something called a table of values, or I could use something called an equation or an expression to help me describe these things. And again, we'll look at what that looks like in a second, but let's quickly just talk about what a table of values means. So when I'm making a table of values, again, what I'm doing is I'm making myself a little table that uses these variables, right? These things that are describing boards and plots. And actually, I'm going to switch those around because usually we see what's called the independent and dependent variables in this order. And we can talk about that in a later video, but just understand that there's a reason I put the P first and the B second. So for one plot, I see that I need 4 boards. And then when I'm looking at 2 plots, I see that I need 7. And when I'm looking at 3 plots, I need 10. And 4 plots need 13. And we can describe this idea of plots and boards given something called a table of values like this. All right. We can also do it using an equation. And the equation is set up in a way that, again, we see the P's and the B's. So the number of boards needed will be equal to, and we can write out some way of adding and multiplying these things together. So again, we have two things happening here. We have this constant 4 that happens every single time. So it's 4, and then to it, we add a number of boards equal to 3 more every single time. So plot 1 needed no boards. Plot 2 needed no extra boards, sorry. Plot 2 needed 3 extra boards. Plot 3 needed 6 extra boards. Now be careful because we have to recognize that if I just said 3p, well, the problem with that is p is 1 in this first one, and that's actually going to give me the 7 that I want in the next one. So in this case, we actually might need to do p minus 1 just to make sure we're getting the right number. Okay, so let's take a look at an actual example that has some questions associated with it. So here we have an airplane. We got an altitude. It's cruising at about 10,000 meters, and it's looking to descend probably towards an airport. So we are given the table of values this time. So instead of having an image, I've given you a table of values. And from this, we're being asked a few questions. So question A says, write an expression for the height in terms of time. So an expression versus an equation, because question B that wants an equation that relates the height to time, an expression doesn't need an equal sign. So we're not actually going to write h equals for the expression. We just want to know what happens. So again, if we're looking at these numbers, we're looking for that constant, that thing that doesn't change. Well, in this case, the thing that doesn't change is the height that the plane started at. No matter what happens after this point, we always know the plane started at 10,000 meters. So it's 10,000 meters, and this is question A, minus this time, because instead of us adding height, we're taking it away. And what we're looking at is how is this plane changing? So notice it changes by 300, right? It descends 300 meters after the first minute, and then it changes by another 300, and then another 300, and so on and so on. And this is the point of these linear relations, is this rate of change, this thing that I'm going down by will be constant. It'll have the same change every single time. Down 300, down 300, down 300. So when I'm looking to write my expression, we're starting at this 10,000, and then what we're doing is we're taking it and we're subtracting 300, but we're not just doing it once. We're doing it once and then twice and then 3 times. And notice this is kind of a repeated addition. It's 300 plus another 300 plus another 300. Well, a repeated addition can be written as a multiplication. So this is 300 times whatever the time I'm talking about. So 300 times 1 gives me this first one, and then 300 times 2 gives me this one, and then 300 times 3 gives me that one, and then times 4 gives me this one, and so on and so on. Now, again, the difference between an expression versus an equation, the equation has to have an equal sign. And that is it. So instead of just writing it out as one thing that's representing height, we are going to make that statement that height is equal to 10,000 minus 300t. It's a very tiny change, but something that allows us to do a little bit more with it. So why do we care about writing an equation for something like this? Well, the reason we care about writing an equation for something like this is because now if I look at questions C and questions D, it's asking me to actually make predictions about this plane's descent. So what is the height of the plane after 15 minutes? Okay, well, now that I have an equation that describes height, so C is h equals 10,000 minus 300t, well, we're being told the value of t. We're being told the time is 15. So now what I can do with that is I can say h is now equal to 10,000 minus 300 times 15, right? We're being told the number of minutes. So what I can do is I can take that 15 and I can plug it into my equation where it belongs. So in this case, it belongs in the place of time. So I get the height is going to be equal to 10,000 minus 4,500. And if I do that subtraction, I see that we are at a height of 5,500 meters. So that's how we would use these equations. And that's kind of the point of them, is now that I have this equation that's describing this relationship of height of my plane and time, I can use it to make predictions about what the plane will do going forward. Question D is asking me to kind of work my way backwards. How long after the beginning of descent does the plane land? So in a question like this, we're not really given a number, but we're left to interpret what the number is supposed to be. What does it mean to land? Well, it means that the height is actually 0. So in this case, instead of being given a time, we're actually given a height. So 0 equals 10,000 minus 300t. And we're being asked to solve for time. So instead of solving for the height given a time, in this case, we're being asked to solve for the time given a height. So those of you that have a little bit of algebra skills, right at this point, what we know we need to do is we need to get this t all by itself. So the first thing I want to get rid of is this 10,000. So I'll subtract 10,000 from both sides. So negative 10,000 equals negative 300t, right? That minus that's in front of my 300 still needs to be there. And then I'll divide both sides of my equation by negative 300. So I get negative 10,000 divided by negative 300 is going to be the time. And this fraction can be simplified. So negative 10,000 divided by negative 300, and I get 100 over 3, or 33 1/3 minutes. Or if, again, we're talking about, we don't really like fractions, right? Like if we were to say 33 1/3 minutes, that would be weird as an answer if you were just kind of talking to someone about time. So 33 minutes, and then 1/3 of a minute is 20 seconds. Okay, so that's kind of the point of these questions. So let's kind of think about what we've talked about so far, and really understand, and then we'll do one more example. So again, when we're doing these linear relations, what we'll notice is that there will be something that remains constant and something that changes. And I can represent that in a couple of different ways. I can represent these relationships as a table of values or as an equation. And when I've found the thing that remains constant, so in this case, the thing that remains constant is the height, notice it is the number in my equation that goes by itself. And we call that the constant. And then when I find the number that changes, so in this case, it's the descent of 300 meters every minute, that is the thing that goes with my variable. So 300 times whatever my other variable is. So in this case, it's t, or time. So let's do one more of these together. So we have Kelly's cabs. The cost of a ride is given in this poster. So we're told that as soon as you get in the cab, you have a fixed cost. You have $3.60, and that does not change. So again, there's my constant. There's the thing that does not change no matter how far I drive. Then to that, we add $1.50 per kilometer. So that is the thing that's going to do the changing. So again, question A is asking for an expression. So we get that $3.60 plus 1.5. And again, it's per kilometer. So we can use whatever variable we want. So in this case, maybe D for distance. Okay. Question B says, now write out an equation. Again, same thing. So it says the fare, how the fare relates to the distance. So fare being what you pay to take a cab. So we'll say F is equal to 3.6 plus 1.5 D. Or in other words, $3.60 is my constant. It's the thing that doesn't change. And then we're going to add to it $1.50 per kilometer driven. And again, the reason for doing this is question C. It now gives us a question that says, now that I know this equation, make a prediction for how much it's going to cost if I want to take an 11-kilometer cab ride. So the fare is going to be equal to $3.60 plus 1.5 times 11. So that's $3.60. And let me grab my calculator here. Oh. So we get 1.5 times 11 and 1650. So we add those together and we get $20.10. And there we go. So that's your intro to linear relations, and I will see you all in the next video.